Our third speaker today is Adnan Hamid from Brecker Verification Systems, and he's the CEO, CTO, and his talk is going to be on ML verification turns convention on its head. Adnan is the founder and CEO of Brecker and the inventor of its core technology. Under his leadership, Brecker has come to be a market leader in next generation functional verification technologies. He has over 20 years experience in functional verification automation, and prior to Brecker, he worked at AMD and Cadence. Adnan holds 12 patents in test case generation and synthesis, and received degrees in electrical engineering and computer science from Princeton University and an MBA from the University of Texas at Austin. So over to you. Thank you, Adnan.
Thank you, Mike. Well, hello and welcome, everybody. I will speak to you a little bit about what these machine learning guys are doing, for those who are not familiar. My focus is on how to generate synthetic tests for these machine learning designs such that we can scale them from simulation to, from unit simulation to system simulation to emulation and post-silicon. Okay. We'll talk a little bit about what these chips are trying to do, the various architectures we're seeing, the challenges I'm seeing these chips have, what planning algorithms are and how they apply to verification. And finally, I'll show you a simplified planning model for a machine learning chip and the kind of tests we get out of them. What is machine learning? Machine learning is basically statistics. I say, if you see a cloud and it rains, you go, maybe clouds cause rain. If through 100 times over your lifetime you see a cloud and it rains, you go, okay, when I see a cloud, there's a chance of rain. So that's all these machines are really doing, right? We give them a bunch of data and tell them what they are looking for, and they build a statistical model, and then later on and that's the so-called learning, and later on you use those statistics to take some real input data and match it against your statistics and try to predict what it is you are dealing with, okay? And you can have this, these AI systems be sort of completely unsupervised. You just throw a bunch of data at it, see what it'll do. And I think we've all heard of some funny stories that have come up on the internet on what happens when you do that. Or it can be supervised where you give it some structure for the kind of thing it's looking for and it's trying to pattern match against that. Either way, the underlying math is that we talk about these neural networks. They're basically a graph of little nodes where each node does some math. Okay, what we're doing is we're feeding the training data in, say 1 bit per input node, and we are getting result data out, and we keep adjusting the weights on these nodes until we get as close to what we want as possible. Then when we get some new data in, we say, okay, with this new data, based on my statistical knowledge of the last 1,000 things I've looked at, this thing looks like, in this case, we're looking at recognizing digits. This thing looks like an 8 to me, or it looks like a 2 to me, or whatever. Okay. The issue is that we want to do machine learning on incredibly large data sets. So people are working on custom hardware to make this work much, much faster than we can with regular hardware. The number of architectures I've seen for these machine learning chips is mind-boggling, right? They all kind of have to do the same thing, but they all look completely different. I've seen designs that each tile is a little SoC unto itself, and they all connect together. I've seen designs where they've built little custom processing elements that know how to do a little bit of work and hand it off to the next processing element. I've seen designs that look like big VLIW engines to me, where it's a very wide computer architecture running the same instructions on different data, much like a GPU actually. Whichever design you look at, they're all kind of solving the same problem, right? Each node is ultimately doing some multiply and accumulate data. And one property of all of these designs is none of them have to run general purpose software. All this technology depends on smart compilers, where the compilers take as input the neural network specification, something like this, whether it's TensorFlow or the 2 or 3 languages that seem to be taking hold for this, and they will compile it down to something that the chip can handle. Okay. Now, these AI chips, they're new, they're different, and the fact is people are trying to figure out what to do with them. And one argument is verification is simply not an issue. We're only going to run what's coming out of our compiler. If we screw up hardware, we'll just fix the compiler, and it's kind of not an issue. Besides, I'm building a design that's the same logic replicated over and over again. How bad could it be, right? I verify one piece, the rest just work correct by construction, right? And of course, we're all DV folks at this meeting, and we all have experience, so we know, right, that if you verify the bits, surely you don't have to verify the system. Everything just works, right? Or not. What is the flip side? These designs are super big, right? So we can't get the full design going even in the biggest emulators that exist. Meanwhile, if we just want to verify a single tile, it's too small to verify the entire behavior of the system. The actual math, we need to verify it, but we're not worried about that, right? Even in CPU designs, we don't worry about the ALU and whether we get our addition correct. We worry about the rest of the control logic that gets the data to the CPU. So there's lots of complex control. There's lots of complex routing, right? What that compiler really is doing is taking the neural network and coming up with a series of operations that routing data all over the design. And that complexity of control logic and routing is where the issues are in these designs. And I watch the project teams themselves struggle with what they should do, right? Many of these AI companies they're not big established companies, right? We don't have 30 years of experience doing this kind of chip. They're all trying to learn what to do, and there's a point of view that says, hey, we'll just have our compiler generate something, and that will be our test. And maybe it's okay. But we're only able to simulate a small, quote, normal case, right? We have no idea what the compiler is spitting out and what the logic behind it is. And it is not possible for that to stress the corner cases for the control and routing that we care about. So to do a good job, we really want to be able to generate synthetic test cases that are focused on doing what is likely to break in hardware. Enter the principle of planning algorithms for verification. So many of you have heard me speak at this forum before, and Recker has been doing these planning algorithms for a long time. What is a planning algorithm? It is the task of finding a procedural course of action for a specific goal while optimizing the overall performance measure. What does this mean, right? So this definition is coming from IBM Watson. What does it mean? It says that we want to write a piece of software that starts with an objective. I want to get a particular value out of my neural network. And then it wants to figure out a plan of steps that will achieve that outcome, where maybe optimizing this overall performance, in our case, is not about get it through as fast as possible, but get it through in as difficult a path as possible, right? Let's make sure that we're trying to do all the control logic that goes around all the math we have to do, and let's make sure that we're trying to exercise all of the routing cases that we have to do. So what do planners bring to verification that we don't already have, right? So I assume everybody on this call is familiar with constrained random numbers for verification, right? System Verilog has brought this to us we've been doing this for the last 20 years or so. We can say, I want to randomize a number, and we can put some constraint on it that says, okay, I want that number to be less than 5. So we know this. What's new? One thing that planning algorithms add is the concept of constrained random control flow. So we can come along and write some piece of code that says, okay, when I get to this action A, I'm going to make a random decision between going to B, C, or D next. So drawn as a graph that can be a decision point A that can go to B, C, or D next. Okay, that's cool. And then we want to be able to put some constraints on that graph. For example, we might say, please do not visit D, right? So that means only legal solutions are B and C. So this idea of being able to come up with randomized control flow sequences is part of the solution that lets us find sequences of operations that'll take us through those neural nets when we have a small portion of the neural net to play with, and we are trying to test the corner cases. The other part of planning algorithms that is important to testing these ML designs is these planning algorithms add constrained random scheduling. Time becomes a first-class element in our in verification. So we might come along and say, okay, in my action A, I want to schedule B, C, and D, and I want to do all of these concurrently. So some tool might come along and say, okay, maybe I have 2 threads and I can schedule these operations somehow. And we can put constraints on the scheduling. We can say, okay, B and C must start at the same time, and B and D must start after B. Okay. So we can define these models for planning algorithms in declarative languages like this new Accelera PSS standard. We can do it in straight C. Language is really not the issue over here. It is simply having ways of describing what it is we want to do. Okay. Once that model is available, then we send a tool off to go generate test cases, right? And what this planner is doing is I say we begin with the end in mind, right? It starts with the outcome it wants, subject to the constraints we've put on the model, and it will synthesize a test case. And it's starting with what it wants to check. It is solving for what stimulus must be driven to be able to check that. It is measuring what coverage through its model it has exercised, and it is dumping some high-level debug information so we can track the nature of the test and what is being verified. And once that test is synthesized, then it can be optimized down to different platforms. So maybe we will take a single tile and run it at the UVM block level. Then maybe we'll take 4 tiles and do kind of a bigger subsystem simulation. Maybe we can take 8 tiles into emulation, and then finally in silicon we'll probably have something closer to 512 tiles or whatever it is, the flavor of the day is, right? And no matter which platform we're running on, we need to correlate the pass, fail, and coverage data and send it back, all back to the coverage closure mechanism. So what do these models look like? Okay. Up here at the top left is kind of the backbone, the top of the model, if you will. And the way these things work is everything is starting at the check, right? We're starting with saying, okay, we want this result coming out of a neural network. And then the tool will backpropagate through that and say, okay, what kind of math am I going to test on this next step, right? Most of these things do multiply, accumulate, but there are various types of operations they can do. So I'm doing the math decisions over there. And then to do that math, I need some inputs, and I'm going to make some routing decisions on where that input should come from. Okay. So if you dig into this, the checking, we're basically saying, okay, go off and do a bunch of these checks. Just figure it out, right? So you're saying schedule these checks. When we're looking at the algorithms, I've simplified the model over here so that it's easy for us to understand. But imagine that we're building out a graph of different approaches to testing the actual math on a single tile, right? Sometimes we're adding, sometimes we're multiplying, adding, sometimes we're doing conditional logic, whatever this guy is doing. And we're making a choice on what kind of operations we're doing. But each of these operations needs some kind of input. Okay? And that request is fed back to this routing guy. Okay? And the routing guy can come along and say, okay, I can pick one of several algorithms that I know on how to route across my little chip. Am I going to get it from the guy to my east, to my west, from somebody far away? And maybe I have to get multiple other tiles to feed me to get my scenario going. And probably the most important line on this little picture that I have for you is the feedback going from the final input over here all the way back to the output of this routing algorithm, right? So basically, the input for that can come from the output of this. So what we're doing is we're saying, okay, for my last stage, I want some result. That means I want, maybe that's the output of tile 0. And to compute this result, I'm going to have the input come from tile 1 and 2. Okay, rinse and repeat. Tile 1 will test maybe algorithm 2, and he'll get his result from tile 3 and 4, and so on. Okay. So what it allows us to do is create some fairly small models that can generate some fairly interesting tests. And when you see the nature of the tests that are spat out of a planner like this, what we're seeing over here is a schedule. We have 4 threads running for this little example. Each of these do checks are the terminal of a sequence, right? Terminal of one scenario. And for example, this check is coming through these algorithms and using this input, and then coming through these algorithms and using this input. And you can see the scheduling that's being done on the different threads to bring the scenario together, right? So imagine that each of these threads are driving on a different tile on the design, and each step in a tile is computing some result that is then forwarded to a later tile or a later slot in a VLIW engine, or a later chiplet in an SoC, right? These guys, they all do different things, but the architecture is always the same. Okay. So in summary, what we're doing is doing concurrent testing that are generating synthetic scenarios that are designed to stress both the math and the routing through these chips. Finally, from there, we want to start talking about coverage analysis and closure, right? So one thing that these planning algorithms are really good at is to take that recursive model and unroll it, right? So in this case, you've unrolled it across 3 stages and said, okay, here are the possible paths I know, right? I can just do a 1-stage check, or I can have a check come from an algorithm that is routed from something else that's a direct input, or I can do 3 stages of algorithm routing to another algorithm, and so on. Okay. So what he's trying to do is come up with the search space, enumerate the search space for all the possible cases that can be exercised, and then we can track coverage on these paths and coverage closure on these paths. So in the end, the hope is that we have exercised every possible type of math, crossed with every possible type of routing, and in theory, we would want to cross that with every possible timing of concurrency, but that might as yet be a bridge too far given the size of the test suite that end up. So to summarize, we talked a little bit about the different architectures we have for machine learning hardware. They all have difficult verification challenges. Planning algorithms give us a scalable solution where we can build a model that goes from block level simulation all the way to full chip in silicon. And that's about it. So thank you very much.
Brilliant. Thank you very much, Adnan. That was very interesting and quite a good complement actually to the other 2 talks. One which was talking about emulation, one which was talking about the verification, the math on here. So it was interesting to hear something that talked about the routing and the algorithms. So one question that's come from the online, have you actually used this on any AI designs, and can you give us just a little bit of feedback from real usage on real AI designs, please?
Yes, we have, and the information that we've shared over here is a summary from multiple designs. It is the test generation mechanics work pretty well. I think my biggest experience over there is these projects are all new. They're dealing with compilers, they're dealing with design styles that are new. So in many cases, it's kind of been the 2 halves of the story is there's, I don't want to say a sense of disorganization, but these projects are trying to figure out what they need to do for the design, how they're going to bring together the simulation, how they're going to bring together emulation. So this is a side that makes it harder to deploy this kind of technology. But what's also become clear is when they don't, and they say, oh, we'll just go with the compiler, they discover at integration levels that they have serious problems. So where this kind of technology has been applied, those integration problems have not been faced.
Okay, so it's applied prior to the integration with the compiler that's going to actually generate the apps that run on this, correct? Is that what you're saying?
So yes, very much the idea is, right, each individual tile needs to be verified by itself.
Okay.
And then you want to take a small number of these tiles and verify that subsystem and then scale up. And really the issues have been in the little stuff works, but then when you start to put multiple things together, they tend to break for silly reasons like designs do, right?
Okay. And have you seen portability of the, one other question, just links to the previous talk, is have you seen scalability from the tests you generate to run a simulation to provide those to emulation? I know it's on your final slide, but have you got any specific examples where you've ported from simulation?
That's yes. So one of the things is that because we're coming at this with portable stimulus, right? We can, once that model is locked in, and the models tend to actually not be huge, right? Because they're recursive, so they contain a lot of knowledge, but they tend not to require a lot of code. Yes, from that one model, you can imagine the recursion. I can just recurse just once, and I can have a really small test if that's good for the UVM unit level. Then we'll put together maybe 4 of these things, and maybe I'll recurse 3 times or 4 times, and I can exercise that guy. Then when I get to silicon, I'll do it on the whole chip, and now maybe my recursion level is set more to something like 512.
Okay, so you can scale as you go from UVM to SoC to silicon. You can scale both the size of the recursions, the size of the test, and the size of the design you're running it on. Correct?
That's right. The schedules get wider, the recursion gets deeper, and also there's another aspect that I haven't punched over here in this presentation. At UVM, we're typically running transactions driving into some kind of VIP kind of thing, but most of these things are software driven, right? So as we get up into bigger portions of the chip, those tests become more software driven, and instead of driving UVM VIP, we're generating C code that's actually running on some kind of embedded processor. Okay. This ability to switch it is kind of a big deal.
Yes, I can see that. Okay, that was the last question we had. So that's good. Thank you very much, and thank you very much for getting